All right, in this video, we continue with chapter 6, section 6.3, and we're going to take a look at non-standard bases and general vector spaces. And so our learning objective for this video is to find a matrix for a linear transformation relative to a non-standard basis. And then we're going to keep proving results in linear algebra using linearity. So it's been a learning objective throughout all of the 3 videos for chapter 6.3. All right, so we're going to let vector space V be an n-dimensional vector space with this basis B equals V1 through Vn. And W is going to be an m-dimensional vector space with basis B prime equals W1 through, I think I should say WM. I think that's a typo there. So we're going to let T map V to W, and that's going to be a linear transformation such that T of V1 for B prime, so we've got a little subscript B prime here, is going to be A11 through AM1 all the way through T of Vn for B prime is going to be A1n through AMn. Or in other words, we can say, in terms of writing it as a linear function, T of V1 equals A11 W1 added through AM1 WM, all the way through T of Vn equals A1n multiplied by W1 added through AMn multiplied by WM, where these A's are our scalars in these linear transformations. So then our m by n matrix, whose n columns correspond to the T acting on the VI's relative to basis B prime, is going to be this matrix A here. And so you can say each column corresponds to our standard matrix A here. And this is going to be such that we can now say, okay, T of V relative to B prime is A, matrix A multiplied by the vectors V relative to B for every vector V and V. So we call A this matrix of T relative to the bases B and B prime. So you can see A is helping us here switch between bases. So let's take a look at this example. We're going to let dx map P3 to P2 be the differential operator that maps a polynomial P of degree 3 or less to its derivative P prime. And that makes sense that the derivatives of polynomials of degree 3 or less are going to be degree 2 or less. Then we want to find the matrix dx using the bases B is 1x, x squared, and x to the third, and B prime is going to go down a dimension and be the basis 1x and x squared. So the derivatives of the basis vectors in B are, well, first we do dx of 1 with respect to D prime. That's just going to be 0 with respect to B prime. So then we plug in our 0 here. So it's going to be 0 times 1 plus 0x plus 0x squared. So that is just all zeros. The yellows are highlighting from my notes when I wrote these by hand. So these are scans. So you can ignore my little highlighting boxes. They came up in the scans here. And that makes sense because the derivative of 1 is a constant. So we expect zeros there. And the derivative of x with respect to B prime, we expect to get a 1 out. And that's just what you see here. It's 1 applied to B prime. So it's 1 times 1 plus 0x plus 0x squared. So we get 1, 0, 0. And then I said here, okay, well, for example, you can think about like a quadratic ax squared plus bx plus c equals 1. Well, what are the coefficients going to be? A is going to be 0, b is going to be 0, and c is going to be 1. So now think about, okay, ax squared plus bx plus c has to equal the derivative of x squared has to equal 2x. So you can see, oh yeah, we end up with this vector, 0, 2, 0. And you can see we're plugging the 2 in here. And then the derivative of x to the third, the 3x squared, is like saying, okay, this equation has to equal the 3x squared. So we get a 3 here. So notice what I called A, B, C are actually in the order CBA, because this is written as an ascending polynomial, and I wrote it descending over here. So here's our standard matrix A. We've got 0, 1, 0, 0 on the first row, 0, 0, 2, 0 on the second row, and 0, 0, 0, 3 in the third row. Now there are 3 rows because we're ending up in a 3-dimensional space, 1x, x2. And there are 4 columns because we started with the basis P3, which has basis, the space P3, vector space P3, which is polynomials degree 3 or less, which has basis 1, x, x squared, and x3. So there's 4 components there. So that's why we've got a 3 by 4 matrix here. Okay, here's my next example. I think, did I miss something? Let's go back. I thought I had something entered here. Okay, here's my example. The internet was a bit slow. So in this example, we're gonna let b equal b prime, which is gonna be this basis 1 cosine x, sine x, cosine of 2x, and sine of 2x. And we're going to let d of x be this transformation from the span of b to the span of b prime. And that's going to be the differential operator that maps a function f onto its derivative f prime. So we want to find the matrix for this transformation d sub x using the bases b and b prime. So here's our derivatives of the basis vectors in b. So the first basis vector is the 1. So the derivative of 1 with respect to x is a 0. And so we see here, well, that's just going to be all zeros because you're going to have 0 times 1 plus 0 times cosine x plus 0 times sine x plus 0 times cosine 2x plus 0 times sine 2x. And then the derivative of cosine x with respect to x is our negative sine x here. And so we're going to get a negative 1 in the middle entry because that is where sine of x is in the middle entry here. And then the derivative of sine of x is cosine x. So you're going to get a 1 here in the second entry because that's where cosine x is in our basis vectors here. And then similarly, the derivative of cosine 2x is negative 2 sine 2x. So we get a negative 2 here in the last entry because that sine of 2x was our last basis vector in the basis. And then the derivative of sine of 2x is 2 cosine 2x. So we get a 2 here in the fourth entry in the column because cosine 2x was the fourth entry in the basis vector. So here is our standard matrix A here for bases b and b prime. And you can see here, just to keep track of things, I denoted like cosine 1, sine 1, cosine 2, sine 2 in the rows and the columns. So you can see here, each of these column vectors, like this one is in the cosine 2 column, and this one is in the sine 2 column because that was the derivative of sine of 2x. And then you could go back and see our other columns here in the previous results. Okay, so you'll work through some similar examples in the group work and the homework, and you are well equipped now for section 6.3.